In the previous module, we have looked into the unit impulse signals. We have introduced unit impulse signals for the continuous time and discrete time case. In this module, we are going to look at various properties of unit impulse signals. Let's consider the discrete time case first. For the discrete time case, an interesting property of unit impulse is as follows. The first property that we are going to look at is called as sifting property. So if we have del of n, the unit impulse signal, to be multiplied with any signal x of n, you'll get the same del of n, but being scaled by the value that is there for the x at n equals to 0. So you can see that if you multiply this del of n with any signal x of n, it simply picks up the value that is present at n equals to 0. So that can be easily seen graphically. So this can be understood graphically that if you have some signal, the simplest signal, let's say if it is 3 to 1, so let this be 3, let this be 2, let this be 1, at 0, 1 and 2, let the axis be n and let the signal be x of n. Now if we try to simply multiply this signal with del of n, so del of n, as we know, is defined only at n equals to 0. So for n equals to 0, it is 1, and for rest of the values, it is 0. So this signal is del of n. And if you see that if you multiply these two, the resultant that we get is this signal. So you can easily see that except the value that is there at 0, the other values are getting directly multiplied by 0. So the value that is there at 0 will be simply 1 times 3, so that is 3. So this signal is x of n being multiplied by del of n. So amplitude here is 3, and we can easily see that this is x of 0 times del of n. So that is simply thrice of del of n. Similarly, we can have the sifting property for the continuous time case. So for continuous time, we have the sifting property as del of t being multiplied by any signal, say x of t, would result in x of 0 being multiplied by del of t. So if we have an impulse signal that is being multiplied with any signal x of t, the resultant, you will get the same signal del of t, but that being scaled by the value of x that is present at t equals to 0. Now this is true for the impulse or its shifted versions. What I mean by that is, this is true for the impulse, or this is also true for shifted impulses. That means if we have, say, x of n being multiplied by del of, say, n minus k, this would give you the same del of n minus k, but now it is being scaled by x of k. So when you have an impulse, a shifted impulse, being multiplied by a signal x of n, it simply picks or sieves the value that is present at kth instance. So it simply results in the same shifted impulse, but being scaled by the value of x that is present at the shift location, that is k. Similarly, we can define that for the continuous time case as x of t. If it is being multiplied by a shifted impulse, say t minus tau, then it would result in the same impulse, say t minus tau, but being scaled by a factor of the x being located at the shifted instance. So x of tau. What is x of tau here? X of tau is a scalar. That means the value of x that is present at tau. Similarly, in case of the discrete time case, what is x of k? X of k here is the value of x that is present at location k. So it's a scalar. That means that the impulse would be getting scaled by the value of signal that is present at the shifted location. Another property that we are going to look at is what is called as the composition property. That means any signal can be composed of the discrete time impulses. So you can see that if we define any signal, say in discrete time case, let's define some simple signal, say the same signal that we have defined here, 3 to 1. If we define the same signal here, so this value here is, let's suppose it is 3, let's suppose it is 2 here, and let's suppose it is 1 at location 0, 1 and 2 for the axis as n, and let this signal be x of n. Then this signal, we can think of this signal as being a scaled and shifted version of various impulses. So you can see that this signal x of n is composed of the impulses being scaled and located at various instances. So we can break down this signal x of n as, say, x of 0 times del of n plus x of 1, that is 2 here, multiplied by del of n minus 1 plus x of 2 into del of n minus 2, and so on. So in general, x of n is in fact composed of the shifted version of the impulses, the shifted and scaled version of impulses. n minus k, where k is running all the way from minus infinite to infinite. So we can see that any signal can be composed of, any signal x of n is composed of shifted and scaled versions of the impulses. Similarly, we can define this composition property for the continuous time case. So if we have this another property, we can define similarly for the continuous time case x of t equals to, instead of summation we'll have an integration there, minus infinite to infinite x of tau del of t minus tau d tau. Next property that we are going to look at is flipping property. It's a very simple property but very important. We can easily verify that x of n is the same as that of x of minus n. The x of n here being the del of n, so del of n here is the same as that of del of minus n, because as we flip it remains the same. Similarly, for the continuous time case, del of t is equals to del of minus t. So if we flip del of n or del of t, it doesn't matter. That is what is called as flipping property of del. There are several other properties for this impulse signal, and the next property that we are going to look at is what is called as a scaling property. So the scaling property is defined as, say if we have this del of at, this is going to be 1 upon mod a del of t. Now I leave this as an exercise to prove this property. We shall see more into such kind of signals in the next module. Thank you.